In this video, I want to talk about ANOVA assumptions, effect sizes, and reporting. So first about assumptions. So ANOVA is a multiple regression model, a general linear model. That means that the assumptions are the same in linear regression. So you already know this because we already discussed this in linear regression. The cases should be independent, which means that you don't want to have repeated measures, for example, in your data. You don't have the same person measured twice unless you do repeated measures in ANOVA or handle this in like a specific way, like with mixed effect models as well. You also want to make sure that you don't have some other type of clustering in your data. So you don't have like twins, for example, in your data that are genetically similar, or siblings or families or things like that. Normality. The residuals are normally distributed. In the concept of ANOVA, that actually means that the outcome variable is normally distributed within each group. Because the ANOVA model, the dummy variables, is basically modeling a predicted effect for a level for each group, or a mean for each group separately. That means in the test assumption we want to look at each group are the residuals normally distributed, or the scores normally distributed. Homogeneity or variance, we also call it homogeneity. Here we assume that the variance is the same across all groups. So each group has the same variance. So the means can be different per group, but we do assume that the outcome variable is normally distributed in each group and has the same variance across all groups. So independence is determined by the study design. You cannot test it statistically. Like, you just have to think about this. Is it reasonable or not? Right? There's some things you can do. You can test for autocorrelation, but like there are so many ways which you can violate independence. There's no possible one way to actually assess that. Normality, we can check with the QQ plots or the Shapiro-Wilk test. Ideally, we do the QQ plots. I prefer not to rely on significance tests, although people do report them a lot in their assumption checks. Homogeneity variance can be tested with Levine's test. It's also available in JASP, where we can test, if the groups have an equal variance. So let's look in JASP for the data that we have. So we go to ANOVA. We had our design, we have a dependent variable here, and two independent variables like this. We got our results, but actually, let's also do some assumption checks. So here we have assumption checks, and we can ask for QQ plot of residuals, which looks good, right? Most residuals look to be normal, which means that on average, the groups are normally distributed. Homogeneity tests, test for equality of variance. We do see a difference here, right? We see a significant difference between variance. Again, it's hard to rely on the significance test alone. In this case, you could also go to the statistics, add dependent variable, and I made a separate grouping variable of each possible combination. So add here, and then I see that the variance indeed, for the real one, the food court one, is like it's a very low standard deviation, which is certainly interesting here. Much lower than this 3.1, right? We ideally don't see standard deviations in here that are more than 2 times another one, or less than half another one. So in this case here, we see definitely that there might be a violation of this homogeneity of variance, but the normality does seem to hold fine. So what do you do when the assumptions are violated? And that's actually a really tricky thing. It's called assumption for a reason. Right? We assume something to be true, even though maybe it's not true. If we assume it to be true, the math works out. If it's not true, then the math technically doesn't work out. It could still be that the math is useful and we still have a very good result. I gave this example earlier in the course where I talked about the probability of 2 people sharing a birthday. We made certain assumptions, like no leap years, but still, like, the math gives a result that is actually sensible. What do we do if an assumption is violated? Non-normality. Well, ANOVA is fairly robust in non-normality, especially with large sample sizes, because of the center limit theorem. So we're looking at group means, and they tend to be normally distributed due to a center limit theorem. So actually that's not that much of a problem. If it's really very non-normal, then it's worth considering. The main thing I would do is I would look at why is it non-normal, right? So maybe there's like a bimodal distribution, for example. And we missed a grouping variable here. Or maybe it's skewed and we're actually modeling like response times or so, and there's a 0 point, and maybe we should take a transformation. This would make more sense. We could transform to the log scale to get a nice normal distribution. Right, so that's worth investigating. The overall slight deviation from normality should be okay. Unequal variances, well, that's much harder to handle. There is something we call a Wells correction with just degrees of freedom. It's available, but it only worked for one-way ANOVA. It doesn't work for factorial ANOVA. So that's a bit of a problem. Non-independence, well, that's the most serious violation. Then you actually shouldn't be using factorial ANOVA, especially if it's repeated measures. For that you have something else, repeated measures ANOVA are mixed models that we can use. And I'll talk more about that in the next week's video series. The general advice, always check your assumptions before interpreting results. Report them. Even if they're violated, report them. And you could still do the analysis and then just say in the discussion, okay, but actually this assumption is violated, so it might be a problem, right? Nowadays, yeah, there are some more complicated things you can do, like non-parametric variance or bootstrapping, standard errors, things like that, that you could try as well. They're hard to figure out, but with the help of AI, maybe you could, more easily figure it out as well. But mostly you want to report them, even if they're violated. You just want to mention those in discussion, okay, normality is actually violated. So this might be a problem or this might reduce the validity of the results. So let's take a look at JASP again. So we had our violation of equal variances here. We should report it, right? And we also saw it in the descriptive table here that the standard deviation is definitely like smaller here compared to the other groups. So we should report that. Can we do anything about it? Well, let's go to assumption check here. Homogeneity corrections. Let's press the button, but it gives an error. And Wells test 2. Actually, there's nothing really implemented in JASP that will allow you to handle this in the frequency setting, which is a bit of a shame. So for now, yeah, if it's violated, there's not actually anything we can do unless you do one-way ANOVA. But, or you do something more complicated, program yourself, there's something in R, but I'm not going to explain it in this course. But yeah, at least this ANOVA is actually quite robust against this, so the result is probably still trustworthy. Some violations of standard deviations of non-equal variances are okay. Here the main problems actually are a small data set. We only have 7 responses here. Maybe we've got more variation if we had more responses. So we want to have equal design, equal sample size as much as we can. And yeah, we should actually have quite some data if we can as well. So that might be an issue here as well. So something we should report in the discussion that it seems to be violated, but actually not much that we can do about it right now. Next, I want to talk about effect sizes. If you find a significant effect, it means that the effect is unlikely to have occurred if the null hypothesis is true. It doesn't mean that the effect is large. We don't know that. Or if it's small, interpretable, or like substantial enough. We can use effect size to quantify the size of the effect. So effect size is something else we can report that basically tells us, okay, this is a large effect, this is a small effect. In ANOVA, so commonly used effect size are the eta squared, the proportion of total variance explained by an effect. That is just like the, how much variance is explained by the main effect, for example. The partial eta squared, the proportion of variance explained by an effect controlling for other effects. The difference is that if we add more like predictors or independent variables, the eta squared might go down because the proportion of total variance there's just more total variance, and the partial eta squared controls for that. And we have omega squared and partial omega squared that are similar. They are basically the proportion of total variance explained by an effect and control for other effects, but they're correct for bias, so they're a bit better. Most people in ANOVA, they will report the partial omega squared because it's interpretable and also because it's independent of how many predictors you add. If you have more, like let's say you add like a third or fourth or fifth variable or covariate, it shouldn't change. So I recommend using the omega squared or the partial omega squared. The rough guidelines are that the small effect would be 0.01, medium effect would be 0.06, and the large effect would be 0.16. 0.14. Some rough guidelines for the omega squared and the partial omega squared, so that the small effect will be about 0.01, medium 0.06, and large be 0.14. So let's look in JASP again. You'll find the effect size right here. We can also include descriptive statistics. Actually, this will also allow us to see the standard deviation per group, which is nice. Let's remove it for now. We can select partial omega squared to obtain this effect size here, which we can then interpret. We see here there's a very strong effect for type, especially like people were able to distinguish the AI generated one from the real ones in this experiment. The last thing I want to talk about is how to report ANOVA, one way of factorial ANOVA using APA style. So you would report the F statistic with the degrees of freedom, the p-value, and the effect size. So you write it like this: F, italic, F, open bracket, the model degrees of freedom, which is called regression degrees of freedom in JASP, of the part you're interested in, like for example the main effect or interaction effect, the residual degrees of freedom equals some value, comma, p, italic, right, these are italic, lowercase p, equals some value, omega squared or partial omega squared, where we added the delta here, equals some value. For example, there was a significant effect for animal type on happiness. F with 2 on 7 degrees of freedom equals 45.16. P-value is smaller than 0.001 and omega squared is 0.19. Or in a factorial ANOVA, there was a significant effect, main effect of condition, right? F2, 81, right? We don't know what depends on sample size, equals some value, P equals some value, omega squared equals some squared value. Right. If the p-value is very low, you would say it's lower than 0.001, for example, which just means that it's somewhere below. You don't say p equals 0, but you never say that. You say it's lower than some value. Yeah, you don't have to include a 0 here because you know that p is always between 0 and 1, so you don't have to include a 0 here. But in the f value, you actually would include a 0 because the f value can be higher. So if f is like 0.18, you say 0.18. Some general APA reporting tips for ANOVA. Report the exact p-values if you can, right? Exact when it's too small to report them. So if you want to round to 3 digits, don't say p is smaller than 0.05. If somewhere else you say p is 0.002, for example, right? This is better. But if it gets so small that you need to round, then report it like this. Always include an effect size, if you can. Use omega squared rather than eta squared, it's less biased, or partial omega squared, which might be even better. Italize statistical symbols, FP, omega squared, degrees of freedom. Round test statistic to 2 decimal places and p-values to 3. Yeah, that would be good practice. The p-value rounded to 3 decimal places is okay. F, you really don't need 3 decimal places there. Right? You kind of want to see if F is larger than 1. So 2 decimal places is really enough. Describe the direction of the effect. So describe in the text also, okay, there is an effect. Then describe it, or better yet, include a plot. Right? Include a plot with like the mean level. And for example, or a bar chart. And maybe you can even add error bars to that. That's a very common thing to do, right? You can think about how you want to do this. Some people make a plot like this, where you basically say, okay, the asterisk showing a significant difference between the groups. Include descriptive statistics, like the means of standard deviations per group in a table or text if you can. So that's it for this video series.